Hey, what's up YouTube? In this episode of the Electric Geo Tracker series, I'll be going over the final major portion, which is building the motor controller. Now, this will be a bit extensive, so I'm going to break up this episode into multiple installments. In the first installment, I'm going to be going over the major components and the purpose they serve. In the second installment, I'll be going over how I actually built the whole controller. And then in the final installment, I'm going to show you guys how I mounted this whole controller box inside the vehicle and the auxiliary wiring that goes along with it. I think that this way, when I split it up, it'll be a lot more palatable. Now, before we start, I'd like to thank this video's sponsor, Indus Precision Manufacturing. They helped out yet again with this video, and if you guys are interested in their CNC capabilities and just their business overall, you can check out the link in the description below. Now back to the video.
Alright, before I talk about the components, I want to show you guys the wiring diagram. This is something I drew up a while ago as my reference. I do want to note that there are two errors here, and I'm going to talk about that in a minute. Let's dive right in. Around the outside, you'll see a blue dashed line. That represents the cutoff boundary where the inside of the controller box meets the outside environment. That's why you'll see all these pass-throughs, for example here, 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 and so on and so forth. They represent a terminal or plug that is a port to the outside. The first component up will be the most distinct one, and that is the motor speed controller. This is the input side from the battery, and this is the output side to the motor. There are a few auxiliary ports like the UART communication ports and the throttle signal inputs. There are a few components that will be the main focus of this video, so I won't get into detail about them. Here is the 0.1 ohm shunt, which will be used for quantitative measurement. If we move a bit over, we'll see the very crucial main contactor, which is a relay. The box you see right here is the main contact, and the switch you see right here is the primary coil. Next, we have the FRM-01 timer modules, and here is the error. I misdrew the output connections and also two unnecessary relays, but I'll go over wiring later. Zooming back out, here you can see the main traction battery that I did a video on, and here is the 12 volt auxiliary battery and ignition switch. These two components supply power to two separate distribution blocks seen here. Of course, another major part is the actual series wound traction motor, which I also did a video on. Other than that, there's a few components that I won't get into, like the throttle, auxiliary relays, fans, and the data display. Alright, so now that I showed you the wiring diagram, let's talk about the main components themselves.
Alright guys, now that I showed you the wiring diagram, I want to now move on to the actual motor controller box. Now, I'm going to go over the enclosure itself at a later time, but for now I want to show you guys some major components that are going into there. These components, of course, are not the only components going in, but they are the most major ones, and I do want to discuss them. It's not really something that I want to glass over, as these components do have important functions that I think is really great for you guys to understand. So, first up on the component list is the contactor. Next up, the FRM-01 module. And then the precharge resistors, and then the current shunt, and finally the most major component, the motor controller board itself. So with these components in mind, I'm just going to go ahead and dive into the first one, which will be the FRM-01 module combined with the contactor itself. So let's take a look at that.
Alright guys, so here is the setup that I wanted to show you pertaining to the contactor and FRM-01 module. So here is the FRM-01 module. I have one here and I have one here. The reason I'm using two is something I'm going to cover in just 1 second. But what this is it's a time-controlled relay. That's all it is. If you look over here, this blue box over here, this is very similar to the 4-pin automotive relays that some of you might see. So in this setup over here, I have it set up connected to my linear power supply and also this multimeter here and this contactor. So let's start with the contactor itself. Now, what is a contactor? A contactor is essentially a really large heavy-duty relay. Usually the inside of here, so below this yellow like epoxied lid, there's some sort of silicon carbide type of sand, and that's just to help insulation. So this relay over here, this contactor, is rated for up to 900 volts and 500 amps. So that's pretty heavy duty. Now you might be wondering, well, why do we need a contactor? Well, in electric vehicles, you need a contactor because this is a electronically actuated, essentially a gateway, keeping, say, a certain current from reaching a certain component. So in our case, this will be activated when you switch on the ignition, and then this will allow current from the battery to flow to the motor controller. And that's where this comes into play. So this relay right here will activate the primary coil of the contactor. This is, like I said, similar to a 4-pin relay. When you activate these with anywhere between 12 and 24 volts DC, it will then close the contacts here. And I also want to note that if you look at the multimeter over here, right now I have it set to continuity check. You can see here it's reading OL, so it is not continuous, as most contactors normally open, aka discontinuous. So let's talk about the FRM-01 module. So there are 18 different operation modes for this specific one, as outlined by the data sheet that came with this. The mode I'm using for this contactor is going to be mode 1, which is delay on, and I'm going to discuss later why I'm using delay on with this contactor. So this will wait 5 seconds when it gets some sort of, let's say, when it gets power. So let's say I were to switch on ignition, right, which is what this would be used for. Once it receives power, it will then count down 5 seconds and then close the relay. So if I shut it off, it will retain memory, and so the next time I turn it on, it will still go through the same settings again. So like I said before, these two leads right here, this one and this one right here, this one, lead to my linear power supply, which is right now set to 12 volts and 2.5 amps, though the maximum spike current that it uses is roughly 0.8 amps, and then it will hold at roughly 15 milliamps once it's the relay is actually closed. So let me show you. So I just switched on the power supply. It's counting down from 3, 2, 1, and then you just heard this relay closing, the contactor closing, and this beep that you hear is the multimeter letting me know that these 2 points over here are now continuous or closed. I'm gonna shut off power supply right now, and if you heard that loud click, that was this contactor opening, and this relay also opening. So now we're going to go on to the precharge relay, and I'm going to tie it into this, and also another use of this FRM-01 module. Now we can talk about the precharge resistor. The precharge resistor is this orange component right here. I have it right here just for demonstration purposes. I have a second one here, which I'm going to discuss in just a second. So let's talk about what is a precharge resistor. Well, a precharge resistor is really no different from a regular resistor. The difference is its function. So it all goes back to the contactor, right? So the contactor obviously has two main contacts over here where the main current will flow through. So on one end of the contactor, presumably over here, you have the main traction battery, which is at roughly 100 volts. On the other end of this contactor will be the motor controller. So the issue that we run into with, well, really any electric vehicle or high voltage setups is that, well, on one end, of course, you have the 100 volts. On the other end, you have presumably 0 volts of the bank of capacitors inside the motor controller. So if I were to activate this contactor right now and have 100 volts just flow right into 0 volts, the electromechanical switch contacts inside the contactor would create an arc flash. And the issue with the arc flash is that that could potentially weld together those contacts, and then those contacts would never open.
If any of you guys have ever accidentally arced, the positive of your car battery to the negative or ground, like let's say the chassis, you've seen it before, that arc flash. And sometimes if it's, let's say, a wrench, you'll notice that it kind of welds the wrench to the body of the car or whatever you're touching. So, now amplify that by, well, that's 12 volts. This is 100 volts. And, your car can dead short roughly 150 amps. This is can dead short roughly 400 amps before the fuse breaks. So that's obviously a big problem. So that's why we need this precharge resistor. Now, as many of you may know, a resistor is a linear element. So it has a set value, so obviously in ohms, and that is that. However, in combination with capacitors, so a RC circuit, right? Resistor capacitor circuit, this becomes a non-linear element. So if you have a resistor between a voltage source and let's say a capacitor, the voltage of the capacitor will slowly rise, as will the inrush current. So that's another reason we use a precharge resistor, to limit the inrush current from when we close the contacts. So that's why we want to use a precharge resistor here. And speaking of which, when I mentioned that there are no special resistors here, this is simply just a lighting module resistor. This is a 25 watt 1000 ohm resistor, and I'll have two of these in series. How I found this out was I calculated how much current will be flowing through here, which would be roughly 7 amps, and due to the wattage, two of them were needed in series in order to bring down the inrush current low enough to where these resistors could handle it. So how is this wired up right now? I have from this side of the contactor, main contacts, I have it going into one end of the precharge resistor, and from the other end of the resistor it goes into the one side of the FRM-01 module, and then it exits out the FRM-01 module from another contact into the other side of the contactor. So this precharge resistor effectively bridges these two contacts, but we don't always want it to bridge these two contacts because, well, resistors will dissipate energy in the form of heat, and well, obviously that's wasting energy. We don't want that. So we want the resistor to be turned on for roughly 5 seconds, which I'll discuss at another time if you guys are interested how I came up with that figure. It'll turn on for roughly 5 seconds, bridging these two contacts together. Then it will shut off, aka close the resistor off to the rest of the circuit. So then the other FRM-01 module will then close these contacts, and then there will not be an arc flash because there will be equalized voltage at either end of the contacts. I know that seemed a little bit confusing, but I want to show you guys how I did it. So if you remember earlier when I talked about the FRM-01 module, I had it in mode 1. This one is on mode 2, so it'll turn on for roughly 5 seconds and then turn off the relay. So I'm going to put the contacts of my multimeter. Right now it's set on ohms. And as you can see here, it reads OL, so these two are discontinuous. And some of you might be wondering, well, why don't I put this on continuity check? Well, there obviously is a high resistance here, 1000 ohms, so the continuity tester would read that it's discontinuous even if it's continuous. So when I turn this on, as you can see, it reads roughly 1000 ohms, and now after 5 seconds it has now become discontinuous. Now I want to show you guys the two setups together so you get why I really use the precharge resistor. Alright, so now I combined the two setups together. This may look a little bit confusing, and I don't blame you. It's kind of hard to clean up this wiring for the video, but I think you get the main idea. All I did was combine the setups from the two previous clips into one setup. So this is the FRM-01 module that's running the precharge relay circuit. This is the FRM-01 module that's running the activation coil for the contactor circuit. And what I'm going to do over here is I'm going to take my
multimeter and I'm connected to the two contacts of the contactor over here. And as you can see, right now it reads OL, so that means these two contacts, as I mentioned before, are discontinuous in its resting state. So when I turn on the power supply to both of these two relays, you'll see what's going to happen. It's going to happen pretty fast, so try not to blink. I'm going to turn it on and I'm going to explain what's happening in live time. So I'm turning on 3, 2, 1. So you can see here right now it's at roughly 1,000 ohms, and these two contacts are continuous. And if you just heard that click, that's the precharge resistor relay turning off, and then the main contactor relay turning on, which then activates the solenoid inside the contactor. And as you can see now it reads 0.1 ohms. So that means these two are continuous, but now the precharge resistor is out of the circuit or disconnected from the circuit, so we don't waste energy through there. I'm going to turn it off and show you guys it one more time without talking. Just pay attention to this multimeter right here. So this is it shut off. That large click you heard was the contactor shutting off, so it reads OL or discontinuous. I'm going to turn it on one more time. So you'll see that these two have it says 3 seconds, but that's a 5-second countdown. I'm going to go ahead and start now. There you go. One more time. All right, I think you guys get the point. So this whole activation sequence is going to happen every time I turn on the vehicle. And like I mentioned before, this is mainly for safety purposes why this whole setup exists. Technically, you don't need this setup to make a running electric vehicle, but you're not going to have one that lasts very long without this kind of circuit. So after I discuss this, I hope you guys get the main point over here. We're going to go on now to talk about the current shunt. Alright, so the next component on the list is the current shunt. Now, what is a current shunt and why do we use a current shunt? So first of all, a current shunt, all it is a very, very beefy low impedance resistor. That's really all it is. If you look really close here, you can see here's the resistive element, and here are the two terminal blocks, and here are the two measurement terminals. So why do we use one? Well, in any system, be it mechanical, electrical, software, you name it, we need some form of accurate measurement of any sort of variable that you really want. In this case, the two most important measurements for this electric vehicle will be voltage and current flow. So how can we do that? Well, we use a current shunt. So as many of you may know, there exists such a concept as Ohm's law, which is V equals IR, or volts equals current times resistance. So this current shunt, really all it is a low impedance resistor with, of course, a known resistance value. So if I slide my multimeter over here and I measure the resistance between these two terminals, as you can see here, it is 0.1 ohms. So if voltage is equal to current times resistance, we can find out the current by finding voltage drop divided by resistance. Since we know the resistance, we can use these two terminals over here, and since if you attach the measurement wires over here that would be wired in parallel, you'd be measuring the voltage between this point and this point, or rather the voltage difference, then you can just simply plug that voltage into the formula with the known resistance, and you can find out how much current flow is going through here. So because your average multimeter only has a current measuring capacity of roughly, let's say, 10 to 20 amps. When you have 200, 300 amps flowing through here, you need something else to measure it, which will be this device right here. So this is the meter that is connected to this current shunt, and it can display a multitude of information. So I have 12 volts hooked up to the backup power ports on here. I'm going to turn on right now.
And if you can see here, probably won't show up on camera too well. Oh, it popped out. So if you look over here, it displays information like voltage, current, power, which by the way, power, if you guys may know, power is equal to current times volts. So that's another useful mathematical equation that you can use to get important data. There's also energy measured in watt hours, capacity measured in milliamp hours. There's resistance, external, internal, and running time, and there's state of charge meter over here. We don't really need all of these from here, but it's really useful to have at least voltage and current measurements so that we can at least quantify any sort of issues that we may run into. So that basically covers what a shunt is and why we're using it, but I hope you guys can see why it is so important. Now we're going to move on to the last component. Alright, the last major component, the motor controller. Now, I'm going to give you guys a quick overview of this, as this whole conversation can get pretty lengthy. I just want to give you guys the basic overview, the pros, cons, why I'm using it, what is it, and so on and so forth. So first off, just to tie in with the last few clips, as you can see here on the motor controller board, there's a bank of capacitors. If you remember me talking about the precharge resistor, this is what I was referring to. These capacitors can have their life greatly reduced if you constantly switch this from, let's say, 0 volt potential to all of a sudden 100 volts. It's not good for these capacitors. Not only that, but of course, as I mentioned before, the contactor can get welded shut. So let's go on to the rest of the motor controller itself. So this basically is a combination of a control or logic board combined with a power board. So there's two main halves of this. I purchased this from a electrical engineering supply company out in Hungary quite a while ago, and this was just a good fit because, you know, some of you who are familiar with electric conversions may know of, you know, known companies out there like Curtis. But those controllers for this amount, for this level of voltage and current, they get quite pricey. This was roughly $265. A comparable Curtis controller would be roughly $1,500 to $1,900, which is quite a bit and just not within the budget. So looking at this again, you can see that right over here, you have some MOSFETs, and then attached to the MOSFETs is a aluminum bar to which you can then place a heatsink because there's these pre-tapped holes right over here. You have these copper bus bars that one end goes in, and that will be the battery, and the other end that goes out will be the positive and negative for the DC motor. And then going over here, you can see the logic board and the intricacies of it. So let's talk about what this motor controller is for. So for those of you that are not so familiar with DC motors or just motors in general, you might be thinking, well, Mason, why don't you just have a switch and just switch on the DC motor whenever you want to drive and switch it off when you don't want to drive? It's not quite that simple. So the operating protocol of this motor controller is something called PWM, or pulse width modulation. Now, what is pulse width modulation? All it is simply you modulate the width of the signal or the duty cycle. So if I had to really try to explain it to you guys, imagine if you had a square wave signal, right, for voltage. If it is, let's say here is 0 and here is 100 over here, right? If it is on 100% of the time, you would say the duty cycle is 100. So also for those of you who are welders, you might know the term duty cycle is how long a certain machine can stay on. So what pulse width modulation is it's the average of the pulses and the width. So for example, if it's on 50% duty cycle, so on 50%, right, and off 50%, that is 50% duty cycle. So what are the benefits of PWM? So the first benefit is that, it's very precise. It is extremely precise and is fast to react. The second benefit of PWM is that it is a digital to analog processor. So what that means is rather than having something mechanical controlling, let's say, your output, you can have something, let's say, electrical controlling it. So you can control this via, let's say, a potentiometer, an Arduino, so on and so forth. And that brings me to this over here. So these dip switches right here determine what operating mode it's in. So for example, if you can see here, this dip switch number 4, when this is switched on, this will turn it onto UART communication mode, which I'm going to go over in just a second. I know there's a lot of confusing terminology here for those of you who aren't familiar with it, but this whole assembly over here, it is programmable. We don't need to program it. In fact, we're not going to program it because for our uses, it's already programmed from the factory basically to how we like it. We will be programming it later on because there's a few variables that we do need to program, such as current limit, ramp up time. These things we'll program later on. So over here, you can see this is the UART communication terminals. The ones we'll be using is ground, VCC or 5 volts, TX, which is transmit, and RX for receive. We will be using it in conjunction with a UART to USB serial communicator converter right here. This will then attach to these ports over here via jumper cables, and this can plug into my computer and then I can program it from there. Alternatively, I can run these the 5 volts ground and TX RX to an Arduino, and then from there use a serial monitor to program it. Like I said before, it's not necessary to program it as is, but it is super helpful. And how we go about programming it really is there is a registry in here, and what a registry is just a way of storing keys, which keys will then store values. So this is why it's so important to be able to read the data sheet, not just as an engineer, but really anyone who likes to tinker with electronics. You really need to be able to read data sheets so that you can find out which key do I pull up to change a certain parameter. So let's say 0x0a will start it in UART communication mode, right? You send that command, and then let's say 0x0b pulls up the current limit parameter, and then we can change it from there. So programming is quite useful. Not to get off on a tangent, but in this case right here, just for simplicity of this video, we're not going to program it yet, but we rest assured we will program some parameters in at a later time. So going back to the power board over here, it's quite beefy. It's got quite a bit of weight. It weighs about 2 pounds. What we're going to use to mount this is, if you see these 4 holes at the corners, we're going to be using 6/32 bolts and standoffs in order to mount it to the motor controller box. And it's going to sit flat with this way facing upwards. We'll have the heat sink over here, and we'll have some fans to cool it down. This controller, if I haven't mentioned it before, is rated for 350 amps continuous and 500 amp peak output. And then anywhere between 48 volts to 100 volts. Well, that covers all the major components. I hope that I gave you guys some valuable information. I know that it seemed a little bit confusing, especially this motor controller part, but I just want to give you guys a quick overview of the major components and why I'm using it. And then so this will wrap up this video, and in the next video, I'll be showing you guys how I'm actually going to go ahead and build this. So I'll see you guys later, and as always, thanks for watching. Bye.